So today we have our very own Nuno, who'll be talking to us about physics highlights from 10 years of the LHC. So I don't think Nuno needs great introductions, but just for new people. Nuno did his PhD at MIT, where he worked on the CDF experiment at the tevatron, and he in particular worked on the discovery of B sub S oscillations, which was one of the major results from the second run of the tevatron. He then was a CERN fellow and Purdue senior researcher before arriving at LIP as an FCT principal investigator. And during this time, from the CERN fellowship onwards, he worked on the CMS on numerous things, from the trigger to physics, where he's worked on heavy flavor, heavy ion, and also long-lived particle searches. And maybe more within this context, more recently, he's been here at LIP spearheading the SHIP and SNE at LHC effort. But yeah, but today we'll hear about CMS. So Nuno, please.
Obrigado. Gustavo, para a introdução. So can people hear me from outside as well? Trying to test my microphone.
Posso começar com isto, se calhar. Desculpa.
Okay, so let's try again. I'm now using another microphone. Can people from outside hear me? So we don't hear a confirmation from the room.
Sorry, can anyone on Zoom confirm this mic is working?
É este aqui, olha lá, é aqui, ou não?
Sim, mas este é o que é?
Sim, yes. Which one?
This one. Is this one working?
Testa lá. Tenta lá agora.
Teste. 1, 2. E este aqui? Este está a funcionar? Ok. Desculpa, não sei o que é. Mas eu acho que este aqui é relativamente perto. Ele te apanha. Assim ouve-se? Assim ouve-se.
Very good. So I hope you can hear well outside as well. All right. So let me then start. So First of all, I don't know if you all realize that we are sort of in the middle of our long LHC journey. So it's, it's amazing that we do. Slides. You know, it's working. Right. So, so I'd like to start, motivating a little bit the LHC. The things that we can do is quite broad, and in fact, we can say now that that we can actually explore all the model particles. So, of course, the LHC is the only place where you can study the heavy particles like the Higgs, the top, and the bosons. But you can actually study all of the other ones. The new arrivals being the neutrinos with these indicator detectors. So the physics program of the LHC then is twofold. So we want to study something called particle interactions to test and over-constrain the same model, and to find and to look for new particles in complementary ways. So so the LHC is the energy frontier machine. So the only place where you can explore the TeV scale for now. But in addition to that, it's also an intensity frontier, which is going to be even more the case now as we enter the high luminosity phase. And this allows us to do extensive precision measurements across a large range of masses, in particular for the electric sector. So the LHC is also heavy flame factory, and it also brings together the ING particle and the ING nuclear physics community. So lots of developments have been done there. There is more recently what is now named as the lifetime frontier. So this is something that is explored also at the LHC in the general purpose, basically to all the detectors. So this morning we actually have a thesis defense on this topic. The LHC also effectively functions as a photon collider, exploring multi-peripheral collisions and with the dedicated kind of detectors. And so the newest arrival is also the study of neutrinos that we can do there. So the LHC sort of not only replaces the tevatron as the leading energy frontier machine, but it also extends and the heavy flame factories, the heavy ion, dedicated heavy ion colliders, and as I'll show, we are actually sort of getting to the level of LEP in terms of precision atomic measurements, which should be impressive. There's a very rich physics program. So there's many papers that we are releasing. So in fact, each atlas in CMS we typically release about 100 papers per year. So this is the quantity. There's also the quality that is ensured. So there is, some would say, many review steps in the collaborations that are ensured in the collaborations. And so this is foreseen by the publication boards of each of the collaborations. I'm serving for many years in the CMS publication board. And here we have distributions of sort of the various areas that are explored. And you see that a good chunk of our papers are from searches. And then next to it you have the measurements from the Sun model and the Higgs. And then, so this is from CMS, but it's kind of representative. And then you have a variety of topics that is covered by the general purpose and the dedicated detectors at the LHC. Now, as a bonus spin-off here, what we have is that we have every year very recent papers that the students of particle physics can study and learn. And actually, I prepared here, in my slides I'll sometimes put this sketch here, and this is to do, it's geared towards the students in the audience, and this is basically to emphasize the connection between the framework that we learn in the particle physics course and the real life that we hear in experimental measurements. So I'll be showing this sketch. So of course the LHC research line has been contributing many research topics over the years for the internship program at LIP, and I just took the ones that I found from the workshop this year. Now back to the schedule. So this is basically where we are, and it's basically about in the middle of the journey. First collisions in 2009. There is this 2041 as the schedule end of the LHC. So we'll lie there in the middle. We also kind of lie in the middle of the current data taking run 3. in that we have collected close to 200 events per femtobarn, which surpasses what we've done in the previous run. So if you put everything together, we had close to 400 events per femtobarn recorded. And in the next years, into the high luminosity, we expect to increase that by a factor of 10, right? So now, of course, the energy at the LHC is not going to increase substantially, but the luminosity is, and this has, of course, implications for the detectors. Let me then mention that. So the data taking here for this, the data taking from this year just ended over the weekend. So with the FDI run, and where we collected a good chunk of data there. As you can see, it was actually a record year for data taking. It went very well. We see here that the data taking rate here surpassed the expectation and collected a good chunk of data, 10% more than target. So this is it. So this was the 10th year of data taking at the LHC, and it ends here with a good performance. So we are collecting great data. And now we just hope that this will be the case also for the next year and a half. That's the remaining time for run 3 that has just been extended into the half of 2026. And after that, of course, we are going to have the new phase, the phase 2 and the high luminosity. For there, we need upgraded detectors. So last week, we had a very nice talk about the upgrade of the tracker. So just like in Atlas and CMS, we're just going to replace completely the tracker, and the tracker is going to feed information into the level 1 hardware for the first time. So that's that, but basically across the board, there's going to be, the detector needs to be completely refurbished. So LIP is involved in, actively involved in the upgrade effort of CMS. In particular, is leading involvement in the new timing layer and in the protein tagger. However, I'm going to refer you to dedicated seminars that happened a few years ago here at LIP about these two efforts and the updates that were given recently in journals. Okay? So this is as far as the contributions to the upgrade. For physics, so the group, so LIP is involved in a variety of topics. We somehow managed to merge everything into a poster that was shown in journals. But now let me then state that, so what I'm going to do today is not going to tell you more or less about any of these results in particular, that the group and myself are involved. So for that we have our occasions like the discussion of the research line strategies and dedicated seminars, and really you can just talk to us about what we are doing. So what I plan to do today, and what we'll be doing, is to give a broader overview of the physics in CMS. Okay? For that I'll do some selected recent results. And this is really the disclaimer. So this is going to be only CMS physics and only a small selection, but it will be nevertheless broad. So let me then start with this generic formula here, that is the cross-section formula, just to relate the physics sensitivity to the factors, to the experimental factors that go into what we can do. So on the left-hand side, what you have is the amount of signal that we are going to observe for a given process, and that depends on the factors on the right-hand side that you want to improve. So the cross-section, of course, is what makes a connection to the theory, but we could increase the cross-section by increasing the center of mass energy, so that's not going to happen at the LHC and for a few decades. But the luminosity is going to increase, and so there's two ways in which the luminosity increases. One is trivial, is that you just keep accumulating data, and the other one is more disruptive, is that we're going to increase the instantaneous luminosity. It is disruptive because you need to deal with things like pileup. So now these two factors then are driven by the machine, while these two here that are related, the acceptance and the efficiency, are driven by the detectors. And again, what you want to do is to be sure that our detector has the proper geometric and thematic acceptance as much as possible, and then that your algorithms and your resolution and your PID capabilities allow us to extract efficiently your signal of interest from the data that that we're collecting. So now this, what I would like to emphasize next is going to be this, the trigger and the DAP system that is, I'll say a few detailed words about that, that are of course critical in the joint environment. Okay, so but let me start then with the first things first, so with luminosity. So luminosity, as I said, so we have a good chunk of data recorded, and 1/3 of it was recorded this year. You see here again the great performance of the LHC this year compared to previous years, that you can go from the slope there. So there's two components here. One is the amount of collisions that the LHC gives us, the delivered luminosity, and then is the fraction of that we keep. And so, and this is all very high, so from both sides. And so which means that we are collecting large quantities of hopefully good data. And so to show you then how this data looks like, and really these plots kind of illustrate why we call ourselves general purpose detector. So you see that we can probe with good precision from the sub-GeV mass scale all the way to the multi-TeV range. And in between, of course, we have all of the electronic sector. And so the detector has the capability, first of collecting the data and then of precisely analyzing across the spectrum. So in addition to the mass range, also the LHC provides different collision energy, several mass energy collisions, and that allows us to probe the dependence of the cross-section on the energy. Now, what I'm showing here is these time-Newman signals, and so you see these striking plots, and so time-Newmans are signals which is maybe arguably the most robust in the electronic collider. But of course, in addition to muons, we use electrons, and we use tau's, and we use jets and photons. So we use all the physics objects, and in addition to that, we also use everything else, right? So we use combinations of vector bosons, stops, Higgs's that now becomes tools for our physics program. And so what you see here is that, in addition to this wide mass range that you can probe, you can also probe many orders of magnitude in terms of cross-sections. And as the data keeps coming in, we are able to probe rarer and rarer processes. And this allows us to probe the standard model, do detailed measurements of the standard model processes, and then look for new structures from particles in different ways, as I'll mention. Right, so the LHC, as I mentioned, also has different collision systems. Proton-proton is the main one, but also heavy-ion collisions, and this allows us to study PCD in different regimes and do searches for new physics in new ways as well. And now we arrive here to the trigger part, and so this is what I want to say a few more words in detail. So, of course, the LHC is delivering us collisions, and then we have a given bandwidth that allows us to select a fraction of those collisions. And that filtering is done, of course, by the trigger system that is composed in these two levels, the hardware level and the software level. And at the end of the day, then, we have these three data streams, right, that I'm showing here. So the one that we mentioned here, normal, so this is the usual thing, right? So we have your trivial algorithm that you tune with given thresholds to keep up with the rate. So the rate here that we are writing this to tape is about 1 kilohertz. And this is how it looks like, right? So in the top right plot, right? So we have here, an inclusive trigger that allows you to collect across the spectrum. But then, if you really want to study in detail a given physics process, you deploy dedicated triggers to study those processes. And here, for example, you see in the color pieces the result of deploying such dedicated triggers for studying each of these resonances and regions. And so that's it. This is a normal strategy for taking data and for triggering. And now there's this other tool that we call here parking and scouting. And by the way, this is also explored by other experiments with different names, but so we call it parking and scouting. And these are alternative ways of taking data, alternative streams that really now they are not really alternative. They become completely embedded in our strategy, and more so as we go into the luminosity. And so, I'll say a few words more about these things that we call parking and scouting. But one thing that you noticed already is that, so we take as much data here with this alternative way, right, 1 kilohertz as well, as we do with the normal. What we also see is that we have been experimenting with this before now we embedded it completely in our data taking strategy. and very famous parking data, parking data in 2018. This was at the end of run 2, which meant that we had like 2 years where we were not, where the LHC was not functioning, and so we had what this allowed us to do is to then, and let me move on to that. It allowed us to process the data then. So what is this thing of the data parking? Is that we collect the data, so there's a new stream in addition to the normal stream that we collect the data, and then what happens to it is nothing. It just stays there. We save it, right? And then what happens then when computing resources become available, the data gets processed. So what this does is that it sorts the bottleneck at the level of computing, right? So we just process the data when the computing resources become available, unlike the normal data stream that is promptly reconstructed. So that's parking, and this allows us to extend our acceptance to things like adjoining final states that we couldn't do otherwise. Okay, so that is one name that we're using, and it's called parking. So the other one is scouting. So what we do with scouting is that we actually can increase the rate, so a few factors relative to the normal stream. And the way that we can do this without disrupting too much our bandwidth budget is to decrease the event size, right? So an example, so imagine that you are interested in studying a process with muons in the final state, all muons in the final state. So then what you do is that, you save only the muons, right? And more than that, you save only the muons that are reconstructed at trigger level. So in this way, we have a very small event content because really we are not reading the data from all your detector elements, so nothing about the colorimeter, we do not need to do that. So this is what this data scouting is about, right? And so now I'm going to illustrate that we actually are doing physics with this and are extending our physics capabilities and portfolio by doing that. Okay, so in here is the first example. So this has to do, we are using the scouting to do a very first observation. So scouting has been deployed in particular for searching for searches since actually 1.1. And now this is actually the first positive observation of such a search. And this has to do with this ether particle. This is not a particle that we use very often at the LHC, but this is actually this peak that appears there, this first peak at 0.5 GeV. And so this is the ether. What we managed to do is that, so actually if you look into those plots, we have quite a lot of ethers there. And if you do a fit, you see that we have about 10 to the 6 ethers decayed into tiny ones, right? So corresponding to this first peak in this pattern that I showed you. Now, if you correct this by the ratio fraction of this tiny decay, it's again 10 to the minus 6. If you divide it into numbers, then 10 to the 12. Now, if you have 10 to the 12 of anything, so I think we will read it, then we'll be able to learn something about that object that we have so many of. And so here what you do is that for this ether particle that was discovered, I don't know, 60 years ago, now we were able to find this very rare decay, and you see it's 10 to the minus 9, which is the ether decay not in 2, but in 4 muons, right? And I don't know if, so this is, we're not supposed to do this, right? So this is a 0.5 GeV particle, right? Just above the threshold for producing 4 muons. And here it is, very clean, very, pretty, very precise, right? And so that's that. So we are able to do this, and we couldn't do it normally. Maybe I should clarify also that the main, I think I already mentioned, the main reason why we deploy scouting is, to do searches, to find, for example, new particles, light Higgs that would decay into muons, and so or into jets or whatever. So we do this. But okay, of course, so we have the scouting, and then we see what nature has in store, and what it had in store. It was not the light Higgs, but it was this rare decay of the ether. And so, and here it comes again. This is supposed to be a bit an aside for the students. But again, the ether is something that we teach students when we apply, formalism, like group theory, to organize diagrams in the eightfold way and so on. And then at the end of the day, we see and we arrive to this part composition of the ether. It's a pseudoscalar octet and all that. So this is the formalism that we teach in class. And now what you can do, and I think it's nice, is that rather than referring to an old particle that was found in pion nuclear interactions, now we are, we can quote and refer to students to a measurement that we just did, that we are doing today, this year, or the previous year. And this should be nice to make this connection between, again, the formalism and real life. So next, what I have is the gypside. Again, this is a famous historical particle, and that's not just because it's the only particle with two symbols. It's that, as you can see, we have plenty of it and plenty of them, and it's a very clean signal that you have there with a very little background. And what you can do with this is that you can do precision physics with that, but you can do more. You can actually use this to calibrate the detector. This is one of the standard candles that we have for calibrating detectors in algorithms. So this is the gypside, if you need an introduction. But now, we know the gypside since a while, but now we again found a very rare decay again of the gypside for the very first time. So this particle has been around for 50 years, and now we found this decay of the gypside into 4 new ones. And you see here, again, the outcome of this analysis. Again, we are not supposed to do this at the LHC, and we can only do it because of parking and all the capabilities that the detector has. So we'd expect this to be done at the charm factory, like the S3, but this is done in this messy environment at the LHC with the general purpose detector. So this should be striking. And so, okay, so here, the historical note that I have here as this side is that, it's November, and that there was a revolution 50 years ago. Actually, there were 2. So one was actually in April, and then I think there was a ripple in November that we celebrated on Monday, right? But there was another revolution in the same month, the same year, 50 years ago, and that was all about the gypside, the discovery of the charm quark, the Kabibu mechanism, gene mechanism, so all about that we teach our students in introductory classes. But here again, you can refer for this peak from very famous otherwise from 50 years ago, or you can choose to show this one from this year. This very nice connection there. Okay, so sticking with the gypsides, because we like it so much, so if you can do well with one, why not trying to discover 2 gypsides, and while at it, why not 3? And so this is things that you can do as we do with more data, and this you can do with gypsides, you can read tops, you can read other particles, but this one, of course, these are easier to produce, and so we arrive there with the lighter states, and these are very precise measurements. You can see that this is a very, you don't find certain amount of processes that give you 6 new ones, and so that's why with a handful of events you can actually claim the observation of more than 5 sigma, and so that's what we do here. I mean, this is nice, we do this because we can, but actually this is important, and so, and then the physics relevant of this is that whenever you're colliding things that are not, that are composite, so then we need to consider that your processes can occur not from single pattern scattering, from 2 patterns interacting, but from multiple pattern scattering, and this is important to understand, to know if you want to understand what you're colliding in the collision environment that you're doing with the LHC. So we started with 0.5 GV, now we ramp up to 5, and then this is the realm of the physics. So I'm going to be quick here. So the dataset we knew, this is a famous decay that we been looking for a long time, and that we found in 2015 with CMS and LHC, and now we have all the experiments that we found. So now what we're doing though is that we are entering a precision phase for this channel. And we are capable of doing precision measurements of the brushing fractions that are very, very small, 10 to the minus 9, 10 to the minus 10. This one, we are still looking for this one. It's hidden there, hidden there. But so we can do measurements of the brushing fractions and of other variables that are sensitive. And here I'm showing the example of the effective lifetime. So, so this brings, this process, the reason why we like it is that it's very sensitive to physics. Through the rates and through other properties like the effective lifetime. So I'm not going to delve too much into these technicalities here, but instead, again, I think this is the last remark that I want to have for the students, is that we have the formalism that we teach in particle physics, and then we have real life. And again, we can make this very nice connection here. So this process is very, very suppressed, and one reason is that we do not have flavor changing intercurrents at real level in the model, so it's suppressed because we have all these vertices. And but half of the reason is that, and the other half is density suppression. And so we typically teach students this using the pion decay. We say that the pion decay to muons and not to electrons, but you can say the same thing here for this. It's exactly the same mechanism is at play, or to put in other words, neither of these should happen at all if the fermions would be massless. So yeah, so this is elements that you can bring from real life happening now into our teaching in universities. So now if we ramp up now in masses and you go to the electroweak scale, around the 90 GeV or at 125, so what we're trying to do here is to probe the spectra, the mass spectra, and again using now not dimuons but the combined mesons and bosons, okay? So what we will try is to see if you find new bumps in the structure appearing and finding rare decays of these particles, of these bosons. In particular here we are using combinations of vector mesons and vector bosons. Here you have the photon, you can also do it with the Z. Okay, so we do that. Now, you can anticipate why it's important for us to do these measurements, and that is that these processes will be sensitive to the couplings of the Higgs with the lighter quarks, with the quarks in general, but with the lighter quarks. There is really no other way one can even attempt to do this at the LHC. And so, of course, you do pay a price. We have a clean signature, but as usual, the price that you pay is that this is very much suppressed. So for now, we do not see excesses there. In these final states, we do see an excess in this one over here. So this is at 125. So this is the first observation of this important rare decay of the Higgs into Zeta gamma that we achieved by a combined analysis of Atlas and CMS data with the run tool. And yeah, so this is really rich. If we can do the same, play the same game and probe different final states. Again, we do not find excesses in general, but if you look into this final state with again our good old GPSI, and if you take two of them, and now we look to see if there is anything decaying in these two that will give you bumps there. So we don't see such structures there in this mass range. But if you widen your search, then you clearly see something going on there, right? So you see the nice continuous spectrum and some activity there close to threshold. So what you do then is to zoom, and if you zoom there, you see this is really above threshold for the production of the GPSIs, and you see quite a complicated structure. So you see that it's not quite so easy to fit. It's not just these three Gaussians that you could put there, and the reason is that there are these dips there. And these dips you can only understand or accommodate by allowing the amplitudes to interfere. But so if you allow for that, you get this nice description. By the way, this is all three collaborations, CMS, Atlas, and LHC are contributing to this effort. But still, what we get is these three new resonances that are all of it. Each of them is a tetrapart candidate, and that's exciting by itself. But more than that, it's actually the first observation of tetrapart candidate that is made out of heavy quarks, in this case of 4 charms. So yeah, and then we enter this realm of finding new hadrons, and this one is a new one that we had to the list. So there's hadrons that we are finding at the LHC. There's quite a good number of them, and the list is increasing. Some are expected, some aren't. We are trying to understand what the nature of these guys are by measuring, by observing them and then by measuring them. But you see that all three collaborations are contributing in this effort. Okay, and so that's UCD. And so now I want to start changing gears, and the question that one can ask is, and that you would ask if you know the answer, but you know what the answer is that whether we have some new, in addition to the Higgs and to these states, hadronic states that we are finding, if we have some new particles from new physics sectors. And so the search here is, there's a comprehensive effort towards finding new physics. We can split it into these direct searches and indirect searches. I think the difference is that here you work with, you produce on-shell particles if you can afford, if your energy allows you to produce new particles on shell, if they're not too massive. Or otherwise, here, this version is cheaper, so you can actually study the presence of these particles virtually, through their virtual contributions. So let me say a few words about each of these strategies. So for the direct search, so what we'd like to do is that we can probe our spectrum in our data. Again, it can be dimuons, it can be dijets, it can be di-Higgs, or top and Z, whatever, right? So we can try to use all objects at our disposal to try to find hints of bumps in our spectra. If you were able to find that, then we just repeat what we did for hints. We measure everything there is to measure about it, the mass, the width, the coupling, and all that. Okay, so we didn't find any sticking signal there in this way. So what can we do? Well, instead of using the physical observables like the invariant mass, we can now replace this with non-physical observables that are however optimized to maximally discriminate between new physics signals and the standard model. And so we use these machine learning inspired variables. Right, so this is of course what we're doing. Still, the answer to the original question is that no, we haven't yet found a lasting resonance anywhere or significant hint of new physics. And so what you can do in that situation then is to prefer your select your preferred physics scenarios. There's many as benchmarks, and then replace exclusion limits on those particles, on those new physics particles. And these limits are around a few TeV. And as you can see, I mean, what we'd like to do, right, we need to extend all these limits both ways. And now going forward in probing massive particles, that's going to be more challenging, just because there is the kinematic limit of the center of mass energy is not going to increase anytime soon. So this is going to increase. We will be able to probe the tunnels, and we will be able to have new analysis techniques, and we'll be able to do that. But this will be slow. It will typically go the square root of the luminosity. But then we can also take care of these empty holes, and this we can do. And this is challenging, of course, but you can try to increase the acceptance to new physics signals. So here is one way how you can do this. So if you look at this sketch here, this is so of course we have our nominal triggers that we call normal triggers, right? That we have our algorithms, and then with a given threshold to deal with our, to respect to not exceed our bandwidth budget. And so as we increase the luminosity, as we will be doing, then we would need to increase also to tighten those thresholds, right? So what's going to happen is that, I mean, it doesn't matter how much data you're going to collect in this region, you are still going to miss new physics if it sits there, right? And so the way that you have to do this then is to extend your acceptance, try to extend your acceptance to not miss this new physics. And this can be done in different ways. One of them is then in this scouting, so these names are going to appear throughout the talk. And so if you do this, so this is a sketch, right? And this is a real life application, and this is a search for like photons, where you use the standard triggers, but you can do that, above, say, 45 GeV, and below that you will be in the dark. But now you use the scouting triggers, and then you can get sensitivity there. And you can go down to, say, 11 GeV. You actually can go down to 1 GeV even. And so the way that you get this exclusion limits then is to looking, as we did for the ETA, looking for these bumps in the dynamic spectrum. And then when you don't see an excess, then you can place limits in different models. This is in physics scenarios. This is again for the same dark photon case. And this is for the Twiggs model. So this is the kind of things that you can do to extend your reach to new physics in our direct searches. There's something more dramatic and more drastic that you can do, which you can refer to as the paradigm shift. And this is, in the early days of the LHC, of course, we wanted to probe the TeV scale, and we were probing, focusing in the masses region that became accessible for the first time. And so we've been looking there, and we haven't found much there. And again, we can't really go much further, faster along this axis. There's another axis, and that's what you can do then is to probe smaller couplings with with intermediate masses. So this is something that you can do. And the way that one way in which you can do this experimentally is to explore the signature-driven long-lived particles. And so what you can have is, you can have a scalar that you produce somehow in your collision, and then because it has a long lifetime, it will travel in your detector, and then it's going to decay there, right? So I work in this type of displaced vertices. And this is a very striking signature, but you keep in mind that this is actually typically outside the acceptance of your algorithms, of your reconstruction algorithms. So this is quite difficult to do, to trigger, you need to calibrate, and you need to use dedicated algorithms that are not the standard ones that you use otherwise, where you assume things come from the primary matrix. So once you do that, though, you can go and place limits. For example, here in the Higgs decay into the pair of these long-lived particles, and then you can place limits as a function of the lifetime of those long-lived particles and also their masses. So just an additional remark about this strategy, and so this is sometimes referred as the lifetime frontier, and so there's an explosion of interest for these kinds of scenarios. And it's followed everywhere, a very active field of study within all the collaborations, in the LHC and beyond, both general purpose and dedicated. And an outcome of that is that there's also new dedicated experiments at the LHC that are deployed or that are proposed, and also beyond the LHC. And so this is also what contributed to the approval of the recent approval of SHIP, which is going to be this general purpose facility for studying these particles in a high intensity regime. Okay, so this is what I wanted to mention in terms of, so it's of course a very extensive program, the searches for the physics directly, but now let me move and talk about the indirect searches, and this has to do with precision measurements. So of course, I mean, here we are going to have saying that we have a process involving 2 quarks and two leptons, and then so we can of course connect them with the standard model, because this is further changing the current that occurs to the loops, as we've seen. But in the loops, you can have standard model particles, but you can also have new physics particles. In this case, some extended Higgs, some new Higgs that can contribute there. Or if you go for something more exotic, you can even have the 3-level contributions there. So at the end of the day, what we actually measure in data, we measure the amplitude sum of all these guys, right? So, I should also say, again, to emphasize that the advantage of these indirect searches is that we become sensitive because we don't need to produce these guys on shell, right? So we become sensitive to energy, to masses of these particles that are orders of magnitude above what we can actually produce directly on shell in your detector. The disadvantage is that it's more difficult to actually pin down the new physics, but for that we have the effective field theory that comes to rescue. Okay, so this is my outreach slide for effective field theory. So basically I can move on and say that this has been very successfully applied in recent years to the flavor sector in identifying a clear pattern of deviations from standard model predictions. And the way that we do this is that we map a large number of measurements into this theory space here of these 2 operators. So this is the Wilson coefficients associated to these 2 operators for this kind of process with 2 quarks into fermions, into muons there. And yeah, so and this is what we can get. So we can then map all these measurements, and so this is what the data maps into this theory space of the Wilson coefficients of these operators. And then yeah, you can see whether your data agrees with the standard model prediction that implies by construction at the origin there. So we did this very successfully with the sector, and of course this is now, you can do this now anywhere else. And if you want to apply it for the Higgs, the difference now is that instead of 2 relevant operators, we have 2,000. And so this is typically the price that you pay if you want to have model independence. Then you have many parameters. Of course, the data doesn't allow us to constrain anything close to this, so you need to make assumptions. Okay, we can talk about the kind of assumptions that are made there. But so basically at the end of the day, what you do is that we have many measurements, in this case for the Higgs sector, right? Many measurements, but many differential cross-section measurements across different decay modes and production modes. And then we try to, correlate all this information in terms of the limits that have to do with these Wilson coefficients, with these CIs, right? So we have about 30, and then we put exclusion limits there. So ideally, if what we'd expect is that, like is illustrated here for the sector, is that 1 or a couple of these Wilson coefficients will start popping out there. Okay, so I think there's lots to be said about effective field theory. I think this is everything I have time to mention. So now, in this way, the precision measurements that you can carry out, then can be interpreted, and the new physics can be explored with this effective. The presence of new physics can be sort of pinned down with the use of these tools like effective field theory. So we can do this for the flavor sector, can do it for the Higgs, as we said, for this, and you can do it for the electroweak, so you can do it everywhere. So now this is as much as I want to mention about the cross sections. Now we also have dedicated measurements of the property of the Higgs. In the interest of time, I'm not going to say much about more about the Higgs. I just want to point you to this paper that Bob Arthur and CMS written a similar one with the status of this scalar, in its 10th year anniversary. So this is relatively up to date. And here I mentioned some updates that CMS is contributing for the mass, the width, and for these rare processes. So that's the Higgs. Now let's move on to a few other interesting particles. So we have the W. So this is a mass, a very recent mass of the W mass. This took a while to do. It's a very long endeavor. So first, the motivation why we want to do this. For this, I can come back to this plot over here. So here you see that in the standard model, the masses of these particles are related. So if you measure the mass of the W and also the mass of the top and the mass of the Higgs, then you can over-constrain the standard model and see if everything matches. And so that's a motivation to do it. Another motivation is that there's a culprit for much of a discussion that has been happening in the community since 2 years, and the culprit is my old experiment, CDF at Graviton. So 2 years ago there was this measurement, and this is striking in different ways. One is that you see it's very precise compared to previous measurements. That's very precise. And the other one, of course, is that it's very far away from the electronic fix, from this fix that I showed you before. So it's about 7 sigma away. And so there's quite a bit of interest to understand where we really are. Of course, we would like CDF to be right. We would like to be in a situation like this. We want to break a standard model, right? That's what we want to do. But so, nature is what it is, and so what we need to do is to do this measurement. So it's a complicated measurement. I can give you more details about that. But in the interest of time, I'm just, So I think I'm going just to move on and mention what the result of this very recent measurement is. I also could add here the reference and the link to the seminar. So we obtained this result over here. And what's striking here is that this is the same precision as CDF. Right? So we managed to get the same precision of CDF. But of course, our result, the CMS result, is aligned with the electrical expectation, the standard model expectation, and not with CDF. I should say, unfortunately. Right? So that's it. So this sort of settles this very active discussion about this anomaly. So the other thing that I want, the very recent measurement as well from CMS is the measurement of this mixing angle. Now, so we can measure the mass of the W as we just did, and of course we can measure the mass of the Z, and okay, that one is easier to do than the mass of the W, so we can measure both. But then if you can do that, of course the ratio in the standard model between these two masses is of course the cosine of this angle, of the mixing angle. And so if you can now have a measurement of the angle, then again we can over-constrain and see if this relation is, if it holds, right? If the standard model is right. And so we do that. So there's this parameter is extracted from the forward backward asymmetry of the Gaussian processes pertaining to muons or of electrons. Again, yeah. So it's a complicated analysis that is done in beams of the rapidity and the mass or in the mass of the electron system. And here are the results, right? And so our result is here, and now you see a pattern that our result is very much compatible right on top of the standard model prediction, which is actually very, it's very narrow here. And the other thing that should impress you, I hope, is that we get a resolution, right, which is a precision, which is very similar, which matches the one that is obtained in plus and minus, right? So and that's impressive, right? That the LHC that we can even try to do that, right? So we are approaching. I mean, we saw that for the mass of the W, we surpassed well the lab contributions, but we are doing this now here as data accumulates. We can improve the precision, the level of precision that is reached at level. As a bonus, what this measurement did is that it also resolved all tension, long-standing tension here between these two most precise measurements there from plus and minus between lab and SLD. And so, yeah, so we are aligned with the standard model, and that tension is also kind of resolved as well. Okay, so another topic. So I'm moving fast because actually I don't even know what time I have because of this minutes that we ended at the beginning. 5 minutes. Okay, wow. Okay. So the top. So this is another fashionable topic of recent, but it's also based on something that that we've been doing all along since a long time. Both and CMS have reported these so-called spin correlations in the top. So we have the top pair produced, and then you can try to infer so the tops are unpolarized, but the spins are correlated, and you can study those correlations by using the electronic decays of the top, of the dot W. And then what you do is that you study the angular distribution, so the distribution of the angle between these two leptons, right? And so once you do that, yeah, so you get this distribution. So we've been, so there's been some surprises in the last several years here that I think we also discussed last time. So now the new thing that appeared is the realization that you can extract from this very distribution this parameter over here, this D, that is related to this metric spin correlation C, and basically the condition for having this entanglement, the sufficient condition is for this raised to be larger than 1, or for this D be smaller than -1/3. So this is the thing, right? So we can extract, we measure the angular distribution, we can extract this parameter, and then we can see, if it satisfies the entanglement relation. So now, what needs to be done? Okay, I'm simplifying things. What needs to be done is that the analysis needs to be optimized for where the region for where entanglement is expected, and that's in the variable mass, just above threshold for TTY production, right? And once you do, then you find here our results. I should say that the first results were found. The first observation was achieved by Atlas in a very nice Nature paper that has been published this year. But then CMS follows suit, and here it's our results. So what CMS did in addition is to include this important contribution from topology. And so that we found that it's important to get a better description of the data. And here you have it. This is the observation of TTY entanglement. Now we have a second measurement, a second paper, where instead of looking into the just above threshold and using the lepton channel, now we are actually using the jet plus, so the single lepton sample, lepton plus jet, and here we are probing the IMAX. And again, so you will find the first observation of top entanglement in IMAX. So okay, so this is a very active area, very excitement, lots of excitement about that, and we have this very nice first observation of entanglement at the highest energy exploring the top decays. So now I'll end with talking about symmetries. So let's start with the CP violation. So this, of course, is a very sensitive process to the physics. So let me just say, quote what we obtained in our recent measurement. So there's two things to say here. So one is that we found the first evidence of CP violation in this precedence decay. And you can see here the data with the 1 to 3 sigma contours, and that they deviate from 0 from the no CP violation hypothesis there. So this is then the first observation there. The other thing is that it's compatible here with the standard model, which is this narrow thing here, which is the standard model prediction. So the other thing, though, that I want to emphasize is that there's flavor tagging. So in order to make this possible, there was a development of flavor tagging, and same site tagging. This is a bit technical, but so I developed this algorithm in the Tevatron, and now what this has been done also at the LHC, and this, as it happened at the Tevatron, and it was critical to find this best mixing. Now we have the same sign taggers deployed at the LHC with this amount of, these are much more powerful than the other taggers. And so what this means is that we have a very nice physics result here, and as data accumulates and we use these exceptional algorithms, we can achieve great things here. Now this is for CP violation in this sector. You can do it in other sectors. Let me just mention about charm. Because I don't have time, I'll just mention that this is our first measurement of CP violation charm. Life is harder in charm. And actually, we're not supposed to do this. CMS was not supposed to do this, and the only reason why we can is again because of this data stream. So we're coming back to these things. This is what I'm trying to emphasize in this talk. And yeah, so we can talk to our LHC colleagues, and they are impressed that we are in the game. But so far, we are the only ones who were able to do this. And now we can too. One dramatic way of finding new physics is to find something where nothing is expected and where a critical symmetry is violated. And you can look for things like Barry number violation or charge lepton violation. For example, here you have this vertex with a single leptonic line, so this doesn't happen in standard model. Or you can have here two leptonic lines but with different flavor. This doesn't happen in standard model. This can happen at production or decay time or at production. So we have optimized analysis for each of these cases. And so this is done in the realm of top that you can be repeated elsewhere. But this is the kind of limits that we obtain for these processes. This is also a benchmark channel, the tau decay into 3 muons. So we are now doing tau physics, but of course you can do it because we have very clean final state in 3 muons and we are good at exploring those robust signals. But this is extremely challenging to do. But nevertheless, by putting together all the heavy flavor sources and the W sources of taus, we can reach a level of sensitivity that is in the same ballpark. You see 10 to the minus 8. Than the best limit that from several years ago from Bell. And so as you can see, as we collect more data, you're going to be able to increase this and surpass Bell. And now there is, of course, Bell 2 is in the game as well. So, but anyway, so here there is a window in which if there's something to be found, so we have a chance of doing it at the LHC in this sensitivity violation case. So we can do this kind of studies across the spectrum. You can do it also for the Higgs. So I'm measuring the Higgs here because although we do not find, so this is the Higgs decay into electron to muon, so although we do not find any such decay of the Higgs, there is indeed an excess there, and it's 145 GeV, and its significance goes to 4 sigma, so that's something to keep an eye on, and that's just what data gives you. So we do many searches, as I've been trying to explain to you, and then sometimes this thing happens. Now either they stay or they go. More data is needed for that. Now I will end with the B sector. Again, these measurements that I'm mentioning now are possible only due to these sparking strategies. And what you do here, so here we're talking about lepton flavor violation, right? Lepton flavor violation. So here I'm talking about something different. It's lepton flavor universality violation. And so this has to do with another axiom of the standard model, which is that the gauge bosons couple with the same strength to the different leptons, so they don't discriminate. What you do is that you compare the rates of the same decay, but to different lepton flavors, like here the mu and the electron, and here the tau and the muon, and then you see if these things indeed match as expected from the standard model. And the reason why we're doing this, you know what it is. So there is indications from LHC that there was violation of this kind of symmetry. And so there's a huge effort that has been coming by the community in CMS to try to do this, and we managed to do it, although it's exceedingly difficult. You can do muons, but electrons and taus at low BP is exceedingly difficult. But so within the uncertainties that we managed to achieve, we do not see indication of the departure or violation of this fundamental symmetry. And now I will end with this blank slide. Actually, the slide is not blank. It's something, but okay, it's something there. But it's good because, so in this square, I'm going to anticipate, it's something exciting happening in this square, and I'll leave you the reference, and I think I can announce that if the organizers agree, that we, not that the paper is out, it was sent last week, so I'll ask you to tell us about this next time, and I will end it.
Thank you very much, Nuno, for this comprehensive overview of CMS physics. Very exciting.